In this video, we'll look at using a trigonometric substitution to evaluate the indefinite integral of the square root of 9 minus x squared. When I look at the expression 9 minus x squared, I'm reminded of the trigonometric identity 1 minus sine squared is equal to cosine squared. I'm pairing the 9 with the 1. I'm thinking of the x squared as the sine squared, and I want to turn that into something like cosine squared. In my formula, in my expression here, I have 9, so I'm going to multiply everything through here by 9. And there I have 9 minus 9 sine squared is equal to 9 cosine squared. What's being squared here is really 3 times sine of theta. And that suggests to me that my substitution should be x equal to 3 sine of theta to match the expression over here. So I'm going to let x be 3 sine of theta. Another way of writing that is saying that sine of theta is x over 3. And that helps me understand the relationship between the variable x and my new variable theta using trigonometry. If I draw a right triangle here, I put theta as one of the angles. The sine of theta is supposed to be x over 3. And by definition, sine is the opposite side over the hypotenuse. So I'm going to label the opposite side x and the hypotenuse 3. The missing side will be square root of 9 minus x squared using the Pythagorean theorem to determine what that length is. Observe that's exactly the expression that motivated the substitution in the first place. Now what we're really doing is declaring a new variable theta, and that variable theta is related to x according to the inverse or arc sine function of x over 3. If sine of theta is x over 3, then theta itself is the arc sine of that ratio. By definition, the arc sine will give you an angle between minus pi over 2 and pi over 2. So our angle theta is in this range of values between minus 90 degrees and positive 90 degrees in degrees, but we'll work in radians. The only other ingredient that we need is the derivative of x with respect to theta. Here I have x is equal to 3 sine of theta. I'm going to differentiate that expression, and I get 3 times cosine of theta. Rewriting that as a differential, we have dx is equal to 3 cosine of theta d theta. We now have all the ingredients in place to carry out the substitution. My integral is of the form 9 minus x squared. X we've decided to be equal to sine of, or 3 times sine of theta. So where I see x, I'll replace it with 3 sine of theta. But remember to substitute out the differential as well. dx is part of the expression. We calculate it to be 3 cosine of theta d theta, and so that will appear in our integral as well. Simplifying the expression, I have 9 minus 9 sine squared, and then I'll carry the 3 cosine of theta at the end. What motivated the substitution was the fact that 9 minus 9 sine squared simplified down to 9 cosine squared. So under the radical becomes a single term, and then we have 3 cosine of theta outside the radical. Taking the square root of 9, I get 3, but taking the square root of cosine squared, in principle, is the absolute value of cosine. Then I have 3 times cosine of theta outside the radical already. Now because my angle is between minus pi over 2 and pi over 2, I'm guaranteed to have an angle whose cosine is positive. This is something that is in quadrant 1 or in quadrant 4 where the cosine is positive. And so I don't really need these absolute values at all, and I'll have, when I simplify here, 3 times 3 gives me 9, and cosine times cosine gives me cosine squared. To integrate this even power of cosine, we use the power reduction identity. It replaces cosine squared with 1 plus cosine of twice the angle, so notice it's 2 theta now, over 2. We expand that out, it's 1/2 plus 1/2 of cosine 2 theta, and we integrate term by term. So I'm going to have 9, 1/2 will integrate to 1/2 theta. The cosine will integrate to 1/4 cosine or sine of 2 theta. Notice that it's 1/4 now, not 1/2, because of the factor of 2 inside the angle. I need to back substitute. I'll need to replace theta with an expression involving x. We already have that over here. Theta is the arc sine of x over 3, so I'll know how to handle that first term. My triangle here tells me how to find sines and cosines or whatever I need of the angle theta, but unfortunately because I've used this power reduction identity, I now have the double angle appearing here. I have 2 theta. So I'm going to need to use a double angle identity for sine so that I can figure out how to back substitute using the triangle. So I have 9/2 theta, and then it's going to be 9/4. I'm distributing the 9 through. And then the sine of 2 theta is 2 times sine of theta times cosine of theta. That's the usual double angle identity for sine. So let's do the back substitution. The theta gets replaced with arc sine of x over 3, just looking over here at our declarations. Then I have 9/2 from the coefficients here. And then in the first brackets, I have to put sine of theta. In the second one, I have to put cosine of theta. I look at my triangle, and I find that the sine of theta is the opposite over hypotenuse. It's x over 3. Cosine of theta is adjacent over hypotenuse. It's the square root of 9 minus x squared over 3, and that is what goes in the last brackets. We've completed the integral. We'll just clean up a little bit. Notice here that there are 2 factors of 3 that are appearing. That will cancel the 9 that appears here. And so simplifying, I'll have 9/2 arc sine of x over 3 plus this expression x times the square root of 9 minus x squared over 2 plus c.